Hi guys, I'm John Baptist. I'm here to present about a dynamic data arrays detector for multi-threaded programs. The researchers who have researched this research paper is Stefan Savage. He's from the Department of Computer Science and Engineering, University of Washington, Seattle. Michael Burrows, Greg Nielsen, Patrick Solborough, and he's from the Digital Equipment Corporation Systems Research Center. And the last researcher is C. Thomas Anderson, and he's from the Computer Science Division, University of California, Berkeley. And moving on with the presentation, if we look at the contents which I'm going to cover today is the introduction first of all, and moving on the definitions, related work, the log set algorithm, improving the logging discipline, initialization and read sharing, implementing eraser, tasks of implementing eraser, representing candidate log sets, performance, program annotations, race detection in an OS kernel, experience, Alta Vista, Vista Cage server, PATL, undergraduate coursework, effectiveness and sensitivity, additional experience, and finally the conclusion. And with the conclusion, the presentation will come to an end. Alright, now firstly let's see the introduction. Which introduction? And if you look at the introduction, in the research paper it is stated that multi-threading has become a common programming technique. As you all know, most commercial operating systems support threads, and popular applications like Microsoft Word and Netscape Navigator are multi-threaded. And if we look at what eraser is, eraser is a tool that dynamically detects data erasers in multi-threaded programs. Eraser simply checks that all the shared memory accesses follow a consistent locking discipline. For many programs, Eraser's approach of enforcing locking discipline is simpler, more efficient and more thorough at catching erasers than the approach based on happens before. It is considered that the eraser is the first dynamic race detection tool to be applied to multi-threaded production server. Moving on with the presentation, if we look at the second content, it is the definitions. If we look at the first definition, it is a lock. A lock is a simple synchronization object used for mutual exclusion. It is either available or on by thread. The operations on lock MU are lock MU and unlock MU. Thus it is essentially a binary semaphore used for mutual exclusion, but differs from a semaphore in that only the owner of a lock is allowed to release it. Moving on, a data array occurs when two concurrent threads accessed a shared variable, and at least one accesses a write, and threads use no explicit mechanisms to prevent the accesses from being simultaneous. Although programs deliberately allow a data arrays when non-determination seems harmless, usually potential data arrays is a serious error caused by a failure of synchronize properly. Moving on with the presentation, if you look at the related work, an early attempt to avoid data erasers was the pioneering concept of a monitor introduced by C.A.R. Hall. A monitor is a group of shared variables together with the procedures that are allowed to access them, all bundled together with a single anonymous log that is automatically acquired and released at the entry and exit of the procedures. Monitors provide a static compile time guarantee that accesses the shared variable and therefore free from data erasers. The happens before order is a partial order of all events of all threads in a concurrent execution. If we look at this figure, this is how it goes. The lock and the variable plus 1 unlock, and it goes to the thread 2. If you look at the thread 2, it goes like this. And the lamp pods happens before order events in the same thread. in temporal order and orders events in different threads if the threads synchronize with one another between the events. Moving on with the presentation, now let's see the log set algorithm. The log set algorithm is how the log set algorithm detects traces. The discussion is at a fairly high level. Techniques used to implement the algorithm efficiently will be described in the next slides. The first and simplest version of the log set algorithm enforces the simple locking discipline that every shared variable is protected by some lock, in the sense that the lock is held by any thread whenever it accesses the variable. Eraser checks whether the program respects this discipline by monitoring all reads and writes as the program executes. And since eraser has no way of knowing which locks are intended to protect which variables, it must infer the protection relation from the execution's history. As you can see in this figure, the program allows a data erase on Y, but the erase not detected by happens before in this execution interleaving. You can see in this figure. Now in this figure, you can see a shared variable is sometimes protected by lock mu1 and sometimes by lock mu2, then no lock protects it for a whole computation. As you can see, the figure shows the progressive refinement of the set of candidate locks for V. When C becomes empty, the lock set algorithm has detected that no lock is protected V. Going on to the presentation, if you look at the improving the locking discipline, the simple locking discipline which is used so far is too strict. There are three very common programming practices that violate the discipline yet are free from data erasers. The first one is the initialization. Initialization is the shared variables are frequently initialized without holding lock. Read shared data. Some shared variables are written during initialization only and are read only thereafter. This can be safely accessed without locks. Read-write locks. Feel like but read-write locks. Read-write locks allows multiple readers to access a shared variable but allow only a single writer to do so. The log set algorithm accommodates initialization, read shared data, and then extends further to accommodate read-write logs. Moving on with the presentation, let's see the initialization read share. There is no need for a thread to lock out others if no other thread can possibly hold a reference to the data being accessed. Programs often take advantage of this observation when initializing newly located data to avoid false alarms caused by this unlocked initialization writes. Refinement of a location's candidate set is delayed until after it has been initialized. What they are trying to say is, since simultaneous reads of the shared variable by multiple threads, if they are not tracers, there is also no need to protect a variable if it's not moving on. If you look at this figure, in this figure the eraser keeps track of the state of all locations in memory. Newly allocated locations begin in the virgin state. This is the virgin state. This is the virgin state. And then as various threads read and write a location like this, they write the location. It changes according to the transitions, like in this figure. According to the transitions, it changes, and the race conditions are reported only for locations in the shared modified state. As you can see, it is the race conditions are reported only for locations in the shared modified state. Now let's let's move on to the next slide. The next slide says the implementation of racer, and it is what they are really trying to say here is, when race is reported, race indicates the file and the line number at which it was discovered and the backtrace listing all the active stack frames. And this report also indicates the thread ID, memory address, type of memory access, and important register values such as programs. And what they are really trying to say here is the race is implemented for a digital Unix operating system on the alpha processor using the atom binary modification system. Racer takes an unmodified program binary as input and adds instrumentation to produce a new binary that is functionally identical, but it includes calls to the racer runtime to implement the lockset algorithm. Moving on with the presentation, now let's see the tasks of implementing the racer. Let's see the tasks. There are basically 4 tasks which are being described in this research paper. The first one is the representing the candidate log sets. The next one is the performance. The next one is the program annotations, and the last one is the race detection in an OS kernel. Firstly, let's see what the representing the candidate log set is. Representing the candidate log set is the implementation of log sets would store a list of candidate logs for each memory location, potentially consuming many times allocated memory of the program. It also catches the result of each intersection, so that the fast case for set intersection simply a table lookup. When a thread accesses a memory location racer files a word by adding a fixed displacement to the location's address. That is what representing the candidate log set is. Next one is the performance. If you look at what performance is, performance was not a goal while implementing racer, but there are many opportunities for using static analysis to reduce the overhead of the monitoring code. In spite of limited performance, tuning racer is fast enough to debug most programs and therefore meets the essential performance criteria. Moving on, the next one is the program annotation. Program annotation is thorough experience. Racer shows that it can produce false alarms. If the false alarms are suppressed with accurate annotations, then when a program is modified only fresh warnings will be produced. False alarms falls into 3 major categories. Those are memory reuse, private locks, and when-in races. It was found that a handful of these annotations are usually sufficient to eliminate all false alarms. That's what I referred in the research paper. And the next one is the race detection in an OS kernel. What I understood by this is, systems that integrate thread and interrupt processing may have less trouble in finding solutions. That's what they are really trying to say in this. And racer can be modified to detect races in spin operating systems, and it was also expected through this technique to detect races between code using standard logs and code using interrupt levels. And next one is the experience. What I learned is the fact that racer work well on the servers is evidence that experienced programs tend to obey the simple login discipline. But through experience, it also was found that racer finds undesirable race conditions in three of the 4 server programs and in many of the undergraduate homework problems. It also states that it also produced false alarms which was suppressed with annotations. Next one is the Alta Vista. Well, Alta Vista is the 2 components of popular Alta Vista are web indexing service, MHTTP and NI2 were examined, and it was found as follows. The MHTTP program is a lightweight HTTP server designed to support the extremely high server loads experienced by Alta Vista. Next one is the Vesta Key server. Vesta Key server is an is an advanced software configuration management system. Configurations are written in a specialized functional language that describes the dependencies and rules used to derive the current state of the software. Next one is the PATL. PATL is a distributed storage system that presents its clients with a huge virtual disk implemented by a cluster of servers and physical disk. Razer doesn't reinitialize the shadow memory for each new stack type, and PATL implements a distributed consensus algorithm as well as failure detection and recovery mechanisms. The PATL server is roughly 25,000 lines of C code. Next one is the effectiveness and sensitivity. Since Razer uses a testing methodology, it cannot prove that a program is free from data erasers. Razer works well compared to manual testing and debugging, and that Razer testing is not very sensitive to the scheduler's interleaving. That's what the researchers are trying to say here. And next, let's look at the additional experience here. Some discipline that avoids deadlock is to choose a partial order among all logs and program each thread so that whenever it is necessary, they can do it in the ascending order. But some programs protect some shard variables by multi-log instead of a single log. Using multiple protecting logs is in some ways similar to using reader logs and writer logs. But it's not so much aimed at increasing concurrency as at avoiding deadlock in a program that contains subholds. Finally, if we look at the conclusion of this research paper, what they are really trying to say is, as the use of multithreading expands, so will the unreliability caused by the data erasers. Hardware engineers have learned to design for testability. Programs using threads must learn the same. Also, this research paper describes about the advantages of enforcing simple locking discipline instead of checking for erasers in general parallel programs that employ many different synchronization primitives. And finally, what really what I personally got through this research paper is, what I really learned is, multi-threaded programming is difficult, and I found that it is error prone. It is easy to make a mistake in synchronization that produces a data erase, yet it can be extremely hard to locate this mistake during debugging. Also, this research paper describes a new tool called Razer for dynamically detecting data erasers in log-based multi-threaded programs. Razer uses binary rewriting techniques to monitor every shard memory reference and verify that consistent locking behavior is observed. We also present several case studies, including undergraduate coursework and a multi-threaded web search engine that demonstrate the effectiveness of this approach. These are the contents which I really learned from this. And by that, it concludes my presentation. Thank you for listening, and I hope this really summarizes the whole research paper. Thank you.